Okay, today we're going to be looking at multimeters and also on a little bit of Ohm's law. So before we're going to be starting a study on circuits and components, and before we really delve into that in any great detail, it's going to be useful to talk about a multimeter. So this here is a multimeter. And they are useful in engineering and in physics, and they allow us to really explore components within circuits. We can use one multimeter to look at voltage, resistance, current. We can use them on AC and DC supplies, and therefore you don't need to have a meter to measure all these different things. This is a pretty bog standard multimeter. You can get really complicated ones. Different multimeters will look slightly different, but this here gives you the fundamental idea behind them. So if you see here, you've got different ranges, and this is the current. So you've got this is 200. This is micro amps, and you've got 200 milliamps, and then 10 amps. Here you've got ohms. This is for resistance, 200. This is 20,000. This is 2,000 kilo ohms. Here we have voltage. This is direct current here and here. And this one here is, you've got a wee wiggly line saying this is voltage for an alternating current. And so as you can see, we can set it to different the range and the area that we are looking to investigate. So the range tells us the maximum reading the meter could give. For example, say you want to read 20 kilo ohms, okay? So you would go to the 20 kilo. That's where you would go, because that's the maximum reading that this part can do is 20 kilo ohms. But say you have 25 kilo ohms, you would go up to the next one, which should be the 200 mark, to 200 kilo ohm mark, to be able to read the resistance. You always select the highest range for the most accurate reading. So again, if we had our 20 kilo ohm, which is here, you'd be able to, if you went here, you wouldn't get a very accurate reading. It might actually not give you the right, it might not appear on the display. So you go to the highest possible range that you can possibly do to read. And generally you would start at the highest and then work your way down. The exception to that rule would be in current, to the direct current reading. But we're going to go through the specifics for voltage, current and resistance in a minute. So we'll explain that in more detail in a minute. So let us think about, firstly, a DC voltmeter. So the first thing you would do, some voltmeters will have a separate button that would give you a power button. This here is the common, this one here is the common input. And you would always connect to the common input. And then for the DC voltmeter, you would do you connect to the voltmeter input, which for this one would be here. So it gives you here, this is the voltmeter DC, make sure it's DC not AC, input. Just to note, some meters have separate current voltage and resistance inputs. So you just need to bear in mind which one it is. And some will have, for the current, you might have like an input for that goes for a larger current, and some will have a low current input. There might be a low input current, and that would be either in milliamps, or it would say maximum 10 amps. This one here, this ammeter is actually this multimeter is actually only going to cope with smallish current, because it says here maximum of 10 amps here. So that's your low input current. And look, it's hard to make out the numbers on this because it's a bit small, the image, but you've got max. So you would need to just make sure you have the right multimeter for the kind of ranges that you would be expecting. So back to, this is for our DC current, so we're thinking it's direct current and we're doing voltage. So you've connected your cables, then we're going to select highest DC voltmeter range. So this would be here. So the highest one, that's millivolts here, where it's got the VM, so it'd be up to here, 1000. Unless you roughly know the voltage that you're going to get, then that would just be redundant. You don't need to do that. Attach the probes across the component you want to measure. So that's really important. If when you're measuring voltage you put the probes in series to the component, you won't get the voltage. It has to be across that component. And then you reduce the range to find most accurate reading. Once you've found the most accurate reading, you note down, it'll show on your display, you note that down. To use an alternating current, you just follow the same instructions for the DC voltmeter, but select the highest AC. So this is your AC, so you select the highest AC voltage here. You be very careful, you never use a multimeter to investigate the mains current coming out of the socket, because the voltage is too high, it's very dangerous, so don't do that. So let's look at an ohm meter. Saying ohm is not easy when you've got a cold. There we go, there we are. So now we connect our input, our common, we still do the common one. And now we do it to the ohm input. Again, this is the same one. This has just got one input for all. Some multimeters will have a separate input for the ohm meter, so you'd connect that to the ohm meter input, and then select highest resistance so on here it is going to be 2000 kilo ohms. Again, if you know roughly what your resistance is going to be, don't do that. Just go to the appropriate range, and then attach probes again across, same as we did with the voltage, across the resistor. Can't spell resistor. Now we say attach across the resistor. All components will have a degree of resistance. So a lamp would have a resistance. So you can measure the resistance of different components as well. They make the then reduce range to find most accurate reading, and then you'll get your resistance, so you take a note of it. And finally, for a DC ammeter. So again, you connect to the common one and the input. Now, connect to ammeter input. Notable point, watch for maximum current, and if there is a separate input for a small current. Now we select the 10 amp DC range. So this is here, this one here, and we connect in series. So unlike the voltage and the resistance, for current you connect in series. That's something that's really important to remember. And you do it at the point that you wish to measure the current. If the current is small, i.e. less than 0.2 of an amp, reduce to a more accurate range. So you'd go down to the 200 milliamps. Now, you only do this if you know the current is going to be small. In the multimeter, there's a fuse. So if the current is larger than 200 milliamps, the fuse in the ammeter will blow. If you go down to if set to a low range. So say you've got a 300 milliamp current and you go down to one of these low ranges, you're going to break your multimeter, so just be aware of that. So that is multimeters, and they will allow us to now really investigate what's going on in circuits and how different components work. So let's look at this in a bit more detail. So we're going to look at Ohm's law. So Greg Ohm was a German mathematician, and he did some investigations into potential difference, current, and resistance. Now, if we have a circuit like this, so this is a battery, and we can change the potential difference. and we're going to study the current. We've got our ammeter, and we've got a resistor here, and we've got a voltmeter. So as we change the potential difference, we want to see what happens to the current and the voltage. You can also leave the potential difference the same and change your resistance and put different resistors in here for different values and see how that affects the current and voltage as well. By changing the resistance in a circuit, we're able to build circuits to do a huge array of different jobs for us, from the light switch to the large particle, the LHC particle accelerator. They all are jam-packed full of resistors. So when you do this, you come across a nice little relationship which you have already met. Plot your graph. This is your current. This is potential difference in volts, and we find that voltage is proportional to current. And this is Ohm's law. So this tells us that voltage has some kind of constant of proportionality that we multiply with to be I. So V over I would give us this constant of proportionality. And we find that this is equal to R, the resistance. So we have the famous equation V equals IR, which is Ohm's law, where V is the voltage in volts, R is the resistance in ohms, and I is the current. Now it's very useful to, and this isn't measured in amps obviously, so if you have access to the ability to build circuits, set up a circuit like this, get your multimeter out and play with it, learn how to use it, take readings for your current, for your voltage, try changing your voltage, try changing your resistance, and see what you get for different readings for Ohm's law. This is quite good at this point just to explain a wee bit more about resistance, because as you're studying electricity you hear an awful lot about resistance. So resistance is a measure of how difficult it is for electrical current to flow. The greater the resistance, the more difficult it is for charge to pass through a material. Current does pass through a resistor, but the current will drop. The current will pass through a resistor, but there will be a drop in the potential difference across that resistor, because the potential, some energy, was used to pass in passing through the resistor. So let's just quickly draw this circuit again, so we can have a look at it. I'm not going to draw I might draw oops, we'll draw our voltmeter. So you've got your current going through this circuit. So you've got our wee electron coming through here, and it gets to this electron, and there's resistance in here. So our electron has to be pushed through here, and to push through here, there's some energy being used to pass it through the resistor. So we then see this drop in potential difference at this point in the circuit. Now resistors are really helpful because some components, you need to control the amount of current that's flowing through certain components within a circuit. And if you didn't have resistors, you would break those components. So resistors enable us to build these circuits and protect our components. Every component has itself an inherent resistance. So the potential difference drops when we attach a lamp to a circuit instead of a resistor. When even the very wires that we have, depending on the material, the type of metal that we're using for these metals, they all have a resistance. I believe the best conductor of electricity is gold, so it'll have a very low resistance, and other metals will have a slightly higher resistance. Copper's got a low resistance, so that's why we use it, because we can't afford to have gold cables. If you've got a very, very sensitive circuit, you really need to, you would need to pay attention and factor in the resistance of the cables. But for most of the circuits that we will encounter, that's not a problem. So before we go any further into talking about different components and different other aspects of circuitry, so we're going to go on to series and parallel circuits, but let us just learn some of the symbols. So in the past circuit, I drew the symbol for a battery. So this is a symbol, this is a battery. Now a battery is made up of a series of cells. So this is a cell. This would have a lower voltage than the battery would, because the battery is basically just a load of these all connected together. Then we have our DC power supply. So we have a positive and a negative terminal, and this is our DC supply. And we also need an AC supply. A common component is a lamp. So you just do a circle with an X in it, and that's your lamp. Also have a motor, which is easy to remember because they helpfully put a big M in the middle of the circle. You can also have a circuit with a buzzer, which you have the two wires coming in, and then we have our buzzer. A way to remember that this one's the buzzer is just think about the sound coming out here. You have a switch. It's a simple on-off switch. You can control the flow of current through our circuit. So you can just imagine when you close it, that closes the circuit, so it allows electricity to flow. And the one that we've just been discussing, our resistor, which is nice and easy. You'll see those all the time in circuit diagrams. We can also have a variable resistor, and we're going to be talking about variable resistors in more detail, maybe either next lesson or lesson after that. So this is our variable resistor. Now variable resistors come in different types. So we have a wee arrow pointing through it. This one here is a rheostat. And we also can have another type of variable resistor. So this one, another variable resistor. And this is called a potentiometer. And we will just be talking about the differences between these two types of resistor very shortly. Then you have a capacitor. Capacitor is basically something that stores charge on these plates, and then it discharges, and capacitors are used in so many different devices. But again, we'll do a full lesson on capacitors. Then we have a diode. Diodes are really quite important in modern circuitry. So it's a bit like a straight line, a triangle with that line going through it, then a wee line here. Now a diode is a component which allows much more current to flow in one direction than another. And there's lots of different types of diodes, and they're used in things like solar panels. The diodes are really quite important in our modern world. Probably the most common type of diode is the light emitting diode, which has the same symbol as our bog standard diode, but it's got two wee arrows coming out, so you can remember that's the light coming off. So this is a light emitting diode, and you probably don't need to look very far round about you right now to see a light emitting diode, because they're really common. We'll have a lesson on light emitting diodes as well. We can also get a photodiode, which is a wee bit the opposite of a light emitting diode, because a photodiode takes in light. Then you have what's called an NPN transistor, which is a type of diode and is used in computing, and we'll have another lesson on these as well, because this is a very important type of diode. We've got a wee arrow here which indicates the flow, and then we put a circle around all this. This is an NPN transistor, but we'll have a separate lesson on one of these too, so it'll help you remember that symbol. A microphone, which is our two connections, a circle and then a line here. It looks a wee bit like a microphone with a little hat on. We have a loudspeaker. There we go. An ammeter, which we've already met today. That's an easy one. A voltmeter, another easy one. An ohm meter, you'll see a pattern because this is an easy one too. And then we have an oscilloscope, which is another easy one to remember because it's just got a wee wiggly bit inside, like an oscilloscope display. Then we have an LDR. I'll draw the LDR first and then I'll explain what that is. So it's a light dependent resistor. So we've got our light coming in here. So this is something that changes resistor. This is something that the resistance will change as light falls onto it. So a light dependent resistor might be used on like a sensor. If you had like a sensor in your garden that would turn on outside lights as when it gets dark, that would have a light dependent resistor in it. And then street lights have light dependent resistors in it. If you think about when the street lights come on as it gets dark at night, it's not that a wee man has turned them on, it's because they're controlled by a light dependent resistor. And then we've got a thermistor, which is another type of resistor, but this, if you think therm is to do with heat, this one is to do with temperature. The resistance changes with temperature. So these are the different components, and again a thermistor would be used in a thermostat in your central heating system. You can set your temperature that you want your heating to kick in, and you're working with thermistors right there. So let's do a little mathsy type problem, and that'll be us. So we want to calculate the resistance of the lamp if the ammeter reads 1.5 amps. So we've got Ammeter, we've got a lamp, we've got 12 volts, and it's an AC supply because we've got a wee wiggly line here, so it's an alternating supply. So we've got V equals 12 volts, current equals 1.5, so we have V equals IR, that's 12, 1.5 times resistance, so the resistance will be 12 divided by 1.5, which is going to be 8 ohms. So I hope that helps.